for that. Yeah, okay. So good morning. So actually today I'm going to talk about the optimal throughput and high short-term fairness design of the renewal access protocol. And then this is a joint work with my student Yoonbae Kim. Okay, this is the outline of my presentation. First, I would like to introduce the Wi-Fi networks, and as you know, the Wi-Fi networks are shared by multiple users, and so if two or more users are transmitting their packets simultaneously, then we have a packet collision. So nobody can transmit the packet successfully. Okay, so in this Wi-Fi network, collision resolution algorithm is very important. Okay? And recently, we proposed the renewal access protocol as a solution of this collision resolution algorithm. Okay? So in the design of the renewal access protocol, we have to consider two important performance metrics. The first one is the throughput, and the second one is the short-term fairness. Okay? So actually, I think you are not familiar with this kind of network analysis. So today I would like to focus on the motivation and the conceptual definition of the two performance metrics, and I will skip the details analysis. And I just provide some main results. Okay, then I will validate my analysis through simulation. Okay, I think everybody in this room uses Wi-Fi network. Okay, so yesterday morning, some of you asked if the Wi-Fi is available in this room or not. Okay, and so here is the example. So we have an access point here. Okay, and around the access point, there are multiple users. Okay, so here is the main characteristic of the Wi-Fi network that we use now. The first one is the air interface is shared by multiple users. Okay. And second, the packet transmission is performed through contention based on a given algorithm that is called the contention resolution algorithm. And actually, nobody knows which user will transmit when. Okay, that is the important characteristics in current Wi-Fi network. Okay, so as you know, contention resolution algorithm is very important. Currently, the IEEE 802.11 distributed coordination function (DCF) is used for collision resolution. Okay, so for your understanding, I briefly explain what kind of collision resolution algorithm we use now. Okay, so first, each station maintains the variable called the back-off counter. Okay, and to generate the back-off counter, each station has a window of size W like this one. Okay, then each station selects a value uniformly from the window, and this value is called the back-off counter value. Okay. Then for the packet transmission, the time axis is divided into slots of equal size, and the back-off count value is decreased by 1 every time slot. Okay? So whenever the back-off count value becomes 0, then the station transmits the packet. Okay? And actually, there are another important characteristic in the current Wi-Fi network. That is actually one of them is maybe the back-off count freezing and some back-off stage concept, but I would like to skip that part today because I want to focus on the selection of the back-off count value. That is the main part in my analysis today. Okay, so due to the uniform selection of the back-off counter, so we avoid simultaneous transmission by multiple stations to a certain extent. That means, here in this example, we have two stations, and station A has 2 as its back-off counter value, and station B select 8 as its back-off count value. Okay? Then in this case, this is the slot time. So every slot time, they are decreased by 1. Okay? So here 2, 1, 0. Okay? And at this moment, station A has 0 as its back-off counter, so it transmits its packet. Okay? On the other hand, station B at this time slot, it has 6, so it does not. Okay? Yeah. So in this case, only one station transmits packets, so this transmission becomes successful. So to a certain extent, like this one, we can avoid simultaneous transmission. But this is not always possible because if both stations select the same back-off count value, then obviously, for example, station B also select 2 as its backup count value, then obviously at this time slot, both stations transmit their packet, okay? And so we have a packet collision. So nobody can transmit successfully, okay? So as you can see here, so obviously the selection of the backup count value plays a key role in performance optimization. So that is the selection distribution is very important. Okay, so in the current Wi-Fi network, the uniform distribution is used for the selection distribution, as I mentioned before. So my main question is, actually, are you satisfied with the current Wi-Fi network? If you are satisfied with the current Wi-Fi network, then you don't need to attend this this presentation. You can go out of this room right now. But if you are not satisfied, if you are not satisfied with the current Wi-Fi network, then you still stay here, and hopefully, hopefully my presentation will help you. Okay. Okay. So my main question is, that is, the uniform distribution good enough for our wireless services? Okay, that is my main question. Okay. So to answer this question, we should consider some criteria. Okay. Here I present 3 criteria. The first one is the high throughput. That means the transmission rate should be high. Okay. So that we can download, upload our video clips as well as emails, so on. Okay. And the second one is the fair location. Okay. That means, the Wi-Fi network is shared by multiple users, so the network should be shared by multiple users evenly. Okay. And the last one is the simplicity in its implementation. Okay. So here, this slide shows the conceptual definition of the throughput metric. Okay. It measures actually the time average number of successful transmissions in the steady state. Okay. In the first example, we have 4 packet transmissions, but one of them is a transmission failure. Okay. On the other hand, in the second example, we have 4 transmissions, but in this case, 2 of them are transmission failures. So obviously, this one is better for us. Okay. Yeah, so throughput is very important. And the second one is short-term fairness. Okay. So this term measures how evenly the transmission opportunities are distributed among stations. So here we have 2 examples. Okay, so in this case, short-term means the time period. Okay, yeah, so if we consider the time period from this to this, okay, then in this example, both stations have 3 packet transmissions. Okay, in the second example, both stations still have the 3 packet transmissions. So in this case, in all cases, the network is shared by all the users evenly. However, if we consider the time period from here to, for example, here, okay, then in example 1, both stations still have equal opportunities. That means both stations have 2 packet transmissions. Okay, but in this case, station A has 3 packet transmissions up here, but station B has only 1 packet transmission. So this is unfair. Okay, so obviously you like example 1, right? So from this point of view, short-term fairness is also very important in the design of the Wi-Fi network. So the purpose of our work is to propose a simple, that means simple to implement, okay, a simple algorithm that provides optimal throughput and high short-term fairness. Okay. To this end, we mathematically model the algorithm by using renewal theory. That is one branch of the stochastic process theory. And we analyze the throughput of the algorithm and optimize it. And we analyze and construct a suitable, the spatial selection distribution that provides high short-term fairness as well as optimal throughput. Okay, so now let's move on to the renewal access protocol. Okay, this protocol is recently proposed by my research group, and actually it was 2 years ago and recently accepted in this journal. So this one is actually a simplified version of the collision resolution algorithm currently used in the Wi-Fi network. Okay, and here in this protocol, a new backup count value is selected from a fixed size window according to a given selection distribution. Here we allow any distribution, not necessarily uniform, as in the current Wi-Fi network. Okay? So whenever station 1 transmits its packet. Okay, so the key question in the design of the RAP is which selection distribution should be used to achieve optimal throughput and high short-term fairness. And in what follows, I will give you the answer. Okay, so hopefully with our analysis, we can improve the performance of the current Wi-Fi network. Okay, for the throughput analysis, we assume the following. So we consider a wireless network with n homogeneous stations, users with the RAP, and each station uses a backup window of fixed size m, and all stations always have packet to transmit. That means all stations are saturated, and so this one is related with the worst case study. Okay, so for the analysis, we take an arbitrary station and we call it the tag station. So T denotes the normalized network throughput. That is defined by the fraction of time the channel is used to successfully transmit packet. Okay, so if you consider the network state, so we have two states, actually the idle state and busy state. Here, during this idle period, there occurs no packet transmission from any users. On the other hand, the channel busy period, and the second one is the channel busy period, where we have at least one packet transmission. And if we have only one packet transmission, then this period becomes a successful packet transmission period. On the other hand, if we have two or more packet transmissions, then this period becomes a collided packet transmission period. Okay? So by observing these characteristics, I would like to skip the detailed analysis. We can obtain this expression for the throughput. Actually here, I is the expected length of this idle period, and BS is the length of the successful packet transmission period, and BC is the length of the collided packet transmission period. Okay, and PS is actually the probability that a packet transmission becomes successful. Okay, so by observing all that, we can obtain this expression. Okay, so to compute this, to compute the throughput, we have to compute this one. But these two, if we assume that the packet size are fixed, then this one becomes constant. So it remains to analyze this part, this term. Okay, yeah, so for analyze this one, obviously we have to consider the backup count value that the tag station select initially, and then we have to follow the decreasing behavior of the backup count value as time goes on. And so the relevant random variable and the stochastic processes are defined in this slide, like this one, x and bt, and y is the intertransmit time of tag terminal, and so using these random variables and stochastic process, we can obtain this our first main result. Actually, the expectation of I is given by this one, and here actually tau. Actually, the expectation of I is a function of tau. Tau is defined by this one, where mu is the average of the selection distribution. Okay, that plays very important in this analysis. Okay, so as you can see here, so remember that the expectation of I is a function of tau, or a function of the average of the selection distribution. Okay, I think I explained this already. So this implies that okay. So I'm sorry. So and the success, this probability PS also expressed by this one. Okay. So as you can see here, PS is also a function of tau. Okay. So this implies that the throughput is a function of tau. Equivalently, T is a function of the expectation of the selection distribution. So here we have very interesting observation from our analysis, that means, higher moment, for example, the variance or the third moment of the selection distribution do not matter in optimizing the throughput, because the throughput is a function of the expectation only, okay? The first moment only, okay? And so from this observation, we can formulate this optimization problem, and actually our original expression can be converted into this nice form, and with this form we show that this is a convex function. Yeah, so we see that we have only one optimal point because this is a minimization problem. Okay, and that one is denoted by tau star. So if we use a selection distribution, any selection distribution with this mean, this expectation, then we can achieve the optimal throughput in your Wi-Fi network. Okay, that is the first part of my presentation. And next, let's move on to the short-term fairness. So to analyze the short-term fairness, we usually use the Jane's fairness index that is defined by this one, where gamma I is the proportion of the amount of channel resource that the I station occupies during a time window of size W. Okay, and actually this one is a number between 0 and 1. So when the index is equal to 1, then we say that we achieve the perfect fairness. Okay, and in our case, in our analysis, gamma I, this one is the proportion of the amount of channel resource that the station I occupies, and that can be converted into the number of the number of success packet transmission of the I station during the time window of interest. Okay, yeah. So at that one is denoted by Ki. Okay, so the index which is originally a function of gamma i's can be converted into a function of Ki's here. And in our case, we assume that we have homogeneous users. So Ki. So in that case, all Ki's have the same probability distribution. In this case, this index is further reduced by this formula, this expression, where only the expectation and the variance of K1 are involved. Okay, but since our objective is to achieve the optimal throughput that is related with the expectation, and so this one is fixed. So in this analysis, we focus on the variance of K1. Okay, so and if we have a smaller and from this expression we see that a small variance would be desirable to achieve the high short-term fairness. Okay, so our next step is to compute the variance of K1. For this one, we consider the relevant delayed linear process. That is actually, this is the time window of interest. The size is W here. And these epochs are the successful packet transmission epochs. Okay. So, and these time epochs are considered as renewal. So we have a renewal process, but actually the first successful transmission is delayed from this one to this one. And so we have a delayed renewal process here. Okay, and by observing this one, we see that K1 is equal to the number of renewals during this time period in the delayed renewal process. Okay, so actually, we are interested in obtaining the variance of K1, so we focus on this part. Okay, so but even though we have a delayed renewal process, but the direct analysis of the process is very difficult. So usually we consider the corresponding ordinary renewal process where the delay is 0. Okay, and so in this slide we consider the ordinary renewal process, and we define these functions and obtain this proposition where this is D is the related with the delayed renewal process, and no D means this is related with the ordinary renewal process. Okay, so we have this one. Okay, so this should be small to achieve high short-term fairness. So this should be small from this result. Okay, yeah, so to compute the variance, it is necessary to have an exact formula expression for pi t. But however, even for the ordinary renewal process, it is very difficult. No explicit expression for pi t. So instead, we obtain the upper and the lower bound in our analysis that are given in the next slide, like this one. Okay, here and here. Okay, and here we have to add up another assumption. That is, z is the inter-renewal time. Okay, so that should be there should be MBUE type distribution. That means, MBUE is the new better than used in expectation. Okay, so actually this is the definition of the MBUE type distribution. Okay, so if Z is MBUE type distribution, then we have this upper bound. So by combining two bounds, we obtain these inequalities. And if you take a look at the lower bound, the first term here, and the upper bound, then they are quite close. Okay, and this one is the probability, so this is relatively small. Okay, so if we make Z the inter-renewal time, MBUE, then two bounds are tight. Okay, and actually this function is very close to its lower bound. Okay, so that means, as I mentioned before, we can achieve very high short-term fairness. Okay, if we take Z or MBUE type distribution. Okay, so but we cannot directly control Z. We can control the selection distribution X that determines the inter-renewal time Z. Okay, yeah, so if we select X that makes Z MBUE, then from our analysis we see that the RAP provides the high short-term fairness as well as the optimal throughput. Okay. Yeah, so here we have very long step to achieve our objective. Actually, here we have 1, 2, 3, 4, 5, 6, 7 steps. Okay, yeah, so we have with these 7 steps we obtain, and finally we know that if we use the Poisson distribution as our selection distribution, then we can achieve high short-term fairness. Actually, the result is quite simple. The Poisson distribution is a well-known distribution and quite easy to generate and implement. Okay, yeah, so and this I do some simulation to validate my analysis. Actually, two figures on the left, we plot the throughput, and two figures on the right, we plot the short-term fairness. Okay, so as you can see here, so maybe it's too small. So here we use the RAP with the MBUE type or the Poisson distribution, then we can achieve the optimal throughput in both cases. Okay. And similarly, if we use the RAP with the Poisson distribution, we can achieve a very high short-term fairness. Okay. On the other hand, if we use the current Wi-Fi protocol, then that falls in this region, okay, which is just much lower than our optimal case. Okay. And similarly, if we use the current Wi-Fi protocol, then they falls in this region. Okay. So which is also much lower in short-term fairness. Okay. Okay, so from our analysis, we see that if the Poisson distribution is used, then we can achieve the high short-term fairness as well as the optimal throughput. Okay, and I think I should stop here. Okay, thank you for your attention.